What if empty space is a loaded gun aimed at reality? Physicists call this a false vacuum, and it can decay. If it decays, the laws of physics could suddenly change. So first up, empty space might not be final. Picture a vast, dark plane of quiet space stretching outward. Empty space here means quantum fields sitting in a particular energy valley. A false vacuum is that valley, stable for now, but not the lowest possible. This matters because particle masses, chemistry, and forces depend on which valley the fields occupy. Quantum mechanics allows fields to jump between valleys, even through barriers, by tunneling. That tunneling creates a tiny bubble of the lower energy valley, which then expands. Think of a metastable atomic nucleus, like uranium, that lasts millions of years before decaying. For scales, calculations put lifetimes far above the universe's age, often 10 to the power of many. Net result: a false vacuum is temporary empty space that can quantum decay into a different vacuum. Imagine a bubble appearing somewhere in space, small at first, then growing fast. The bubble separates two different sets of physical laws, inside and out. That boundary is a wall where field values change sharply, and it moves outward near light speed. Anything caught by the wall would find particle masses shifted and forces altered. Stars and planets inside the bubble would no longer obey familiar chemistry and nuclear physics. For numbers, the wall travels roughly 300,000 kilometers per second, so nothing can overtake it. So if a true vacuum appears, it converts whatever it touches to new physical laws. There is one field that matters most here, the Higgs field, which gives particles mass. The Higgs potential is an energy landscape with valleys and hills, and its shape decides stability. Quantum corrections from heavy particles tilt that landscape, changing barrier heights and depths. The top quark and Higgs masses feed directly into those corrections, so precision measurements matter a lot. Small shifts in those numbers can turn a high barrier into a lower one, raising tunneling likelihood. For example, current data often imply metastability, not absolute stability, with lifetimes far longer than cosmic time. Bottom line, the Higgs potential largely sets whether our vacuum is false or true. Physicists turn the problem into a quantum tunneling calculation in field space. They find a so-called bounce solution that connects valleys and compute its action. The decay rate depends exponentially on that action, so small parameter changes cause huge lifetime swings. Numerical simulations scan possible field configurations and include quantum corrections from many particles. Experimental uncertainties, particularly the top quark mass, produce enormous lifetime ranges. For instance, a slight percent change can shift lifetimes by orders of magnitude, often around 10 to the power of 10 or more. So precise experiments and careful theory together decide our vacuum's safety margin. If a true vacuum bubble reaches Earth, there would be no conventional warning. The wall would sweep through in less than a second, and it travels at light speed. Atoms entering the new vacuum could find binding energies altered, and nuclei could disintegrate. Chemical bonds might not hold as before, and molecular structures would reorganize or collapse. Energy release from changed bindings could be enormous locally, but it depends on specific field values inside the bubble. Bottom line, a bubble wall passing Earth would change physics instantly and destroy structures as it crosses. At first that sounds terrifying, but the answer is effectively no, for realistic experiments. Cosmic rays regularly produce collisions far more energetic than human colliders, and they have done so for billions of years. If those collisions could nucleate a fatal bubble, nature likely already triggered it somewhere. Colliders concentrate energy in tiny regions, yet their energy scales remain far below thresholds for new vacua in most models. Preventing decay would mean changing fundamental parameters, which is not practical. So human-triggered vacuum decay is not a realistic concern, given cosmic precedent and current theory. Even if decay is extremely unlikely today, the idea reshapes big-picture questions about laws. It forces us to ask whether constants are fixed or environmentally selected across many universes. Studying metastability drives more precise experiments and sharper theoretical tools like renormalization group flow. It also bridges particle physics with cosmology, because early universe conditions could have selected our current vacuum. Some explanations invoke a multiverse where only certain vacua host observers, giving an anthropic selection effect. So false vacuum thinking pushes both experimental work and philosophical inquiry into why our vacuum sits where it does. We began with a startling claim: empty space could be unstable. Current data suggest extreme longevity, not imminent doom. If you liked this deep dive, subscribe for more curious physics stories. One-line takeaway: our vacuum may be metastable, but it probably lasts far longer than we do.